Okay, hey everyone, how you doing? It's good to be back. I've been away for a few weeks. I was actually deep diving into some advanced TypeScript books, and then I've been away for a romantic holiday in Iceland, so that's been nice. And so now I'm back and looking forward to jumping into some Rust. So I thought I noticed there's this Google Kickstart competition running with a practice session, and so I thought, why not try to find a nice way to scan standard input with Rust. And then I came across this guy on Codeforces who's already implemented a scanner or a reader writer. So I thought, why not use that? So they've got this GitHub here with a bunch of different data structures and things like that. But they've also got a scanner. And I mean, coming from Golang, it's the same thing. You have the reader writer interface, which is a nice abstraction which everything uses to interoperate with files and all kinds of things. Anything that you need to write to and read to with a buffer. Um, so yeah, you can see they've made the implementation here, and then they've got a test down here. So maybe it's easier to look at the test to see how it works. So they've just got some input. So in competitive programming, you usually get input through standard in, and it might be one number on each line, or each line might have a series of numbers that represent the problem, and then you also print out your solution after parsing the input. So they've got some numbers here and some strings, and you can see 10 here. Maybe that represents that there's 10 numbers on the next line. So they've got n as the U size. So Rust is automatically inferring that this is the U size, and it can read that. So that's quite cool that it knows it's a U size, not like I32 or anything else. And then there's a vector of unsigned 64-bit integers, and once again it's inferred that, which is quite nice. And we can see how this works up here. There's this read method, and so it knows the return type is T, and so it knows that this is T, which is any type that can map from a string into its own value. So it has to implement this from string trait, and it's basically just skipping spaces and new lines and so on. And then it's just taking whatever characters it can, as long as they're not any like spaces or new lines. And then it's collecting them into a vector, and then just turning that into, I guess this is turning it into a string, and then parsing that. And then it's just, I mean, it's just going to blow up and say parse error if it can't parse it into the type that you're wanting it to go into. And then you can see there's a few other methods, like getting a vector of a certain type, or getting some characters instead of a string. So yeah, let's give this a go. And yeah, they're just representing standard input here, but I'm just going to copy from their submission on Codeforces. So it looks like they've, perhaps I'll just copy all of this somehow. Copy. Cool. And I'll just delete some of this in a sec. But yeah, let's go to the problem first. So just let's just see. So we have a few different problems. So I'll just go for milk tea since it's worth the most points. Yeah, so there are many either or options to customize milk tea. So with ice or no ice, with sugar or no sugar, with bubbles or no bubbles, and so on. So the preferences can be represented as a binary string. Ones are names. What else? Sugar, no bubbles, no pudding. That's it. So 1, 1, 0, 0. Yeah. So any friends not here. Instructor offers P binary options. Looking at one's preferences. And too complicated. But the same type of T for everyone. Yeah, so n different orders. They will complain once. Every preference that is not satisfied. Okay. So you're 1. They'll complain that. So they complain once, and this one they'll complain twice. The n different forbidden types of empty. Okay. What is the smallest number of complaints that they can get? Okay. To n and NMP and lines each of which contain a binary string. Preferences and friends. And more line each of which contains a binary string. Okay. So this first test case, there's 3 friends and 1 forbidden order. So that. There's 4 just means these are all 4. We'll just solve this by hand. So these are the 3 orders. So I guess the first thought is just to do something greedy where we just pick the most popular order. That so we look for each type of milk and so on. What is the milk that most people want, and just get that. So we can see how many 1s there are. So there's 2 1s in the first digit, and then there's 1 1 in the next digit, 1 1 in the third digit, and no 1s in the last digit. And then the zeros, there's 1 in the first digit, 2 in the second, 2 and 2. Oh, 2 and 3. Okay. So I guess we'll probably run into something that's forbidden. So we want this to be a 1 because there's 2 people that want a 1 and only 1 person that doesn't want a 1. So that's be a 1, 0, 0, and 0. And this is forbidden. So it seems like we need to do breadth of search or Dijkstra's. So every time we change one of these numbers, I mean, if these numbers are equal, then we can change it for 3. Whereas if they're not equal, then we're going to upset more people than we please. And so the cost to change a 0 to 1 or a 1 to a 0. So to flip one of these bits, we can work out the cost by looking at the difference between these 2 numbers. And so if I try I'll try flip this bit, and then I'll try flip this bit, and then I'll try flip this bit, and then I'll try flip this bit. And so we'd get 0, 0, 0, 0 for the first flip, and then the next flip would be 0, 1. That should be 1, 1, 0, 0, and 1, 0, 1, 0, and 1, 0, 0, 1. And so I'd look at these, I guess if this is a step of Dijkstra's algorithm, then these will be in my heap queue with their associated cost. So each time I flip a bit, I can modify the cost. And so in the heap queue, I'll store the cost and the state, and the state is this Uh, so how many? So these can be up to 100 grams, up to 100 forbidden items. So there's only 100 forbidden orders, which means our search won't last for very long. I mean, worst case, we'd search for 100, and the first 100 we look at, they're all forbidden. And yeah, I think, or maybe it's slightly worse than that, but yeah, we should pretty quickly find something that's not forbidden. And yeah, each time we flip a bit, we make it slightly worse. And we just have to watch out for duplicates, because if I flip bit one and then bit two, and then another time I flip bit two and then bit one, then I'll get a duplicate. Just need to make sure I don't go to the same state twice. So let's say all of these were forbidden as well. Then I would have go from 0, 0, 0, 0 to its children. It should be 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, and then this at the same time, this one would go to, which is this one, would go to, we'll flip the first bit, flip the second bit, third bit, fourth bit. So you can see that these are duplicated, and actually these are even duplicated with the very first one. And then yeah, there you go. So I guess we can code this up. And I do have to go in like half an hour probably. Hopefully, should be 10. Okay. Again. Yeah. So this is the number of test cases, and then we got 3 numbers. Okay. So we don't really need them. And then just using print line. There was a right method. Yeah. So we had N and P. I need to scan in binary strings and then n binary strings. I could use that. But yeah, I can't, because it's going to think this whole thing's a string. So I could get all the chars using this chars method. I kind of want, I could use true and false, but I kind of want to add these numbers together, because here I counted how many ones and how many zeros there were. So I'll just use, so I'm just going to add a new method to the rector. The binary, what's it called? Binary digits, binary. Let's call it binary Corey is your right. So I'll use bytes. Each byte will not go into the between either one or zero. So 3 minus so that'll map the 0 to 0. Wait, do I even need to do that? Yeah, I think we do. Okay. Now scan these. So orders surface works. I should try this right method. So how does right work? What is S? Yes, anything that can you that has a two-string method. I'll just use print line. Sample, but works. Very basic. That's okay. We don't need the yeah, looks correct. Cool. All right. So I could write some code here to solve it, but I prefer to make a helper method called solve. Because if we have a complicated bug or yeah, we can create some simulations and call solve with our simulated input rather than having to generate standard input every time we want to test it. So this makes it a bit easier. So we have our orders. What was it? Was a vector of what we saw the tricky. So yeah, it is. Someone's at the door. Okay, I'm back. Luckily, I'm not streaming, so I was able to pause. Someone came to pick up some furniture, and they're quite early. It was good exercise carrying things down 2 flights of stairs. Right, so we just built this Solve helper that takes some orders, which these vex of UH, which are kind of like binary strings, I guess. And then we have some orders which are forbidden, and then we have P, which is just the maximum, the length of the order. Sorry, yeah, the number of different types of bits, I guess, in each string, the length of each string. Okay, so I need to, let's see. Um, what does it need to return? Um, let's see, the output. So we just output x, case number. Why is the minimum number of complaints? Okay. The our solve method will just return usize, which is the number of complaints. Return 0 for now. Or just say unreachable. Since we're doing Dijkstra, we'll just keep going until we find something. What happens if we never find anything? Because this is to the p minus 1, it means, I think it means we'll always find something. We can't forbid every possible type of order. And I mean, I can't see -1 anyway. Yeah. Well, we can just submit and see if we get the right answer anyway. Once it's ready. Okay. So, cool. So for each test case, we've scanned input, and now we will go. Let's see that right. So S is anything that implements two-string. So yeah. And usize implements two-string, I'm pretty sure. I actually do have some hotkeys to navigate back and forth. It's mind square bracket. So there we go. Oh, actually, what is the format? So there's a new feature where you can go like this. But I think the version of Rust that Google's running is probably too old for this. So let's go like this. I guess it's a little too strong. Um, I need this person. It starts from one. Let's just return two. So let's see what happens. Cool. So now we need to do Dijkstra's. So we need a set of all of the bit strings or bit vectors that we've seen. So we'll use hash set, and we need a heap. Use number versions hash set. Binary heap. And we'll make forbidden a hash set because we want to look up if it's forbidden or not. So just reassign it, which is kind of a nice thing. And then I won't do this too often. So, I'm getting a lot of messages to pick up furniture. I already sold it. So hash set, okay. Hash set. Use parameter. So that's quite cool. I thought we'd need to import this, but I think in your versions of Rust you don't. But I think when I submit, I'm going to get a compiler. We'll find out. I'll probably forget about this at the end, and I'll wonder why it's not open. Okay. So consuming a bit into this hash set. 20 box slots. That's not what I want. Is when autocomplete changes. I mean, you press enter and then it changes, and then it presses the enter event runs, and it doesn't select what we wanted. Okay. So got a set of forbidden items. What's this question mark here for? I'm not sure why it's complaining. Oh, that's great. I'm not sure what I'm doing wrong. So I need to count the zeros and the ones. We'll pair them. Some of the ones. So these need to be mutable. Now I need to build so I can greedily see for each index what is the preference of everyone. Like, just coming back to the example. So I've got the this and this, and now I can say, okay, there's more, two is bigger than one, so that this should be a one. So that now. Zeros, it's very bad. Not greater than equal doesn't really matter. So, oh, there's lots of zeros, and lots of people want a zero, so we'll give them a zero. So start add equals zero, which is what we don't need this because it's the default, but it doesn't matter. And then yeah. And then I also need the cost, the number of components. So the number of components. Oops, that's 3 components. Oops. For all the people that wanted a one, but they got a zero. So it's the converse of that. What am I doing? Okay. So this is the answer. If it's not forbidden. So now we do our dexters. We also need to keep track of what we've seen so far. So we need a hoop. Almost use the fact DQ. I don't really do dexters much. It's pretty much the same thing. This H. What is it? Okay. We have count. Okay. So our node needs to implement, needs to be orderable or comparable, I think. Make a struct and implement ordering and things like that. I'll just use a tuple. So we want the least number of components first. And this always trips me up because in Python the heap goes smallest. We pop the smallest first, whereas in Rust we pop the biggest first. And I want the least number of components, which means I want the reverse of endpoints, and then I'll just have the bit vector too. So reverse is quite cool. I guess it's kind of like a smart pointer or something, but it will act just like an I-32. But when you try to compare it, it'll flip the two inputs that are getting compared, which means this binary heap will give me the least amount of complaints first, which is what I want. So I'm moving, so this is copy. So this will just get copied by value since this is an I-32, whereas this is getting moved. So when I put, so I need to put this into here, so mark it as the same, and I need to put it into here. So I'm going to need to do a clone. So same, but maybe popping from the heap, popping check what points. I guess so. Points. Not sure all this. I'll just call it order. So if it's not forbidden, then great. That's all it's forbidden. Order. The order is not forbidden. And we want to return the number of complaints. This is the smallest number of complaints we have in the heap since we're doing smaller stuff. And actually, this is, I think this is reverse. I don't know why it's not telling me what this is. I'm actually not sure how to get the value out of it. Usually there's like an inner output method or something. Got 0. So it's just a tuple with a value. I can just, I guess that's the name tuple. Let's go dot 0. Let's just see if this works. Oh. Okay. Oops. And then, okay, that's supposed to do this for each order. So sorry, it's sort of been confusing too now. I'm watching for each order and orders. So now we've got that. But consume this. We won't be needing this anymore. Expected one generic item. Okay. I was wondering what the IntelliSense was struggling. Okay, so now it knows what's what. This should be reference. Those would consume the order. This is looking good. Yeah. Come on, but I'm not sure what I'm doing wrong here. What's wrong here? No, yes. So I consume step before I even fund it. So if I swap the order of those two ones, and I'll just swap the order of these two. This is not very forgiving. Cool. So it's working. All right. So now what we need to do is the final step, I think. We need to, for each order, since it must have been forbidden, we want to search for other orders nearby that are not forbidden. Well, they may be forbidden as well, but so we need to flip all the bits like I showed. So in this step here, we start off with this is the current order that we're at, and then we need to generate all the child orders by flipping a bit. and recalculating the cost. Someone's at the door. One sec. Sorry about that. The guy that was picking up the furniture came back and he wanted to buy some more furniture, but he was trying to lowball, so he was offering far too low. But anyway, that was interesting. So where were we? So yeah, we were gonna find these child nodes, right? So for each bit in the order, we need to flip it. So for child order equals order needs to be mutable. And we'll flip the ith bit. So f order 0 just child order 1. Those will flip a 1 into a 0. Let's see. So we need to adjust the cost as well. So we've got the number of complaints there. So what happens here? We change a 0 to a 1. So now all the people that wanted a 0 are going to complain. So they will complain. All the people that wanted a 1, they will no longer complain. It's implicit or built into this complaints number. We previously had this plus this, and then so to swap them, I guess I think that works. Okay. In other words, it's the other way around. Okay. So now I've built things, now I need to add them into the heap. But I also need to check they haven't been seen before. So if I haven't seen this step before, because remember we had some duplicates here. Like for example, this one would have already been seen. I don't want to add it to the heap twice. Seen contains. Yeah, if it doesn't contain it. Child order. Need to insert it. I guess we need to clone because we're adding it to the heap as well. So we're adding it to 2 places, so we need 1 clone. And it's also worth mentioning when we insert it into the heap, it'll be up to log in comparisons. And the comparison will compare first on the cost, and then on it's going to compare the second item of the triple, which is up to length 100. So it is kind of expensive. Like each time we're doing these things, it's costing us 100 because these can be up to 100 long. But I mean, if Rust is up to 100 times faster than Python, and then I mean, it should pass. And yeah, because m's not very big, this doesn't happen that many times. I think it should be. I'm pretty sure this would be pretty quick. But if we did want to optimize, there is a 128-bit number in Rust, but it's kind of, I think it's still experimental. I'm not sure. But we could use two 64-bit integers, and if if I is less than 64, then we add it to the one integer, otherwise we add it to the other. So we use some like bits, and then we just have a tuple of two 64-bit integers. And that would be quick for comparisons or for hashing to look up in the same structure. So we could have our own custom hash. And also for the heap queue, I mean, instead of storing this whole bit vector, we could have just stored an index that represents that bit vector. Yeah, or we could have just created our own struct that implements ordering and partial equality and equality and things like that, and then tell it be able to look at this. So we could definitely improve this code, is all I'm saying, but I think this should be fun. It's good. Well, inserting it into sense that we never want to look at it again. And then also we need to add it to the heap. So Kickstart push. And so the cost is the reverse of actually, I wonder if this even works. But I think I need .0 here, right? Over. Reverse links and the child order. Okay. And this won't work because it's already being put into the scene. You can't put it somewhere twice. So, it's quant. Okay. I think I'm done. Let's see. What do we want to see? We want to see 4 and 2. Need this. Cool. 4 and 2. And then I did say maybe we could compile with using this formatter. Let's just try to submit this anyway. Moment of truth. Now I need to figure out how to submit. How do I submit? What? This is strange. Download the static code. Submissions. feel like there's a bug or something. This is frustrating. I feel like maybe I'm just not seeing it. Download this starter code. Sure, problem. I'm just going to pause this for a second. I'll try to find out how to submit. Okay, so I found out why I couldn't submit. I wasn't registered. You have to register with Kickstart. And then once you've done that, this submit attempt appears. Oh no, looks like maybe my screen's cropped. Okay, so let's try to submit this. But yeah, I'm expecting a compile error. Test mode? Test run mode, yeah. Testing mode. So I'm worried my screen was cropped the whole time I recorded this video. So that's a bit of a bugger. It's a compile error. So tell me what compile error was. How do I see what the compile error was? It doesn't even tell me. Oh, yeah. Before, so fit it in. Yeah, that's what I thought. So from edit. Oh, there they are. Just that one. Okay. Let's try this. Cool. So that ran. So that's the moment of truth. Let's try to submit. Awesome. So worked first time. So thanks everyone for watching, and good luck to anyone who decides to take part in Google Kickstart. It's often a bit of fun, and yeah, sorry that the video was a bit cropped. I guess you couldn't see any of my output down the bottom, which I have. I'll just show you. You can see this is what you were missing the whole time, but I didn't really use the console too much, so hopefully the video still makes sense. And yeah, thanks a lot. Feel free to subscribe if you like. And yeah, I'll stop recording.